All right, so let's see if we can do an example where we have to do a two-tailed F-test for whether or not population variances are equal. So this is actually from the previous section, section 7.3, where we were looking at whether or not the means were equal. Notice the reason why I kept this in the stem of the problem was, notice it says that at the very, very end, it says assume that the variances are equal. If you're going to make that assumption, you better have a way to test whether or not that assumption is actually a valid one to make. So really what I'm doing here is, this is actually problem 7.4-11, part A. 7.4-11 has you go back and look at the problems in 7.3 and see whether or not the assumptions that the variances were actually equal was a valid one to make in those individual problems. So you might want to take a look at a couple of those just as sample problems to make sure that you understand the idea here and how to do these types of hypothesis tests. All right, so I'm going to do this one completely in Excel so that I don't have to write anything down. I'm going to type along as we go, so bear with me if I make errors. I am not re-editing these videos. Too much to do to try to get everything online, so I apologize if these aren't, high quality videos, because I made such high quality ones before, as you, I'm sure, all knew. Even if you couldn't tell, that was sarcasm. All right, so anyway, we want to test whether or not the variance for X and the variance for Y are equal versus unequal. So for unequal, that is two-tailed test. So that's why over here, what I've got labeled is I need a lower F value and an upper F value, because remember that the F distribution, if you remember the graph of that from the previous video, the graph was not across the y-axis. It's not symmetric across the y-axis. So I have to have a lower value and an upper value to be able to divide it into two tails, much like what we had to do for the chi-squared distribution when we were doing tests for variances, individual variances, I should say. All right, so let's get our sample statistic for the sample variances. So remember, again, to do this in Excel, I'm just going to hit equals. I'm going to use VAR. We want the sample variance, so we'll do the VAR.S. And I literally just want the variance for these. So A11 through A19. That gives me that one. And for the second one, same command, except that I want to do the y's. So I'll highlight those and get that variance. This is not new. We've done this before. All right. So when we do our test statistic, we'll just do the ratio of these. In this case, since we're doing a two-tailed test, whether or not one variance is different than the other, it really doesn't matter which one we put on top and which one we put on bottom, because we're going to have two different critical values that we're going to compare it to. Either it's going to be too low or too high, and that's all going to just depend on which one you put on top. So it really doesn't matter which one we do, as long as we know how to do the interpretation correctly. All right, so let's go and figure out how we do the critical F values. All right, so remember that we need a numerator degree of freedom and a denominator degree of freedom. So when I do my test statistic, I'm going to do X over Y. So my numerator degrees of freedom, there are what? There are 9 of these here, and there are 13 of the Y's. Remember, we have to subtract 1 off of each of these. So there's 8 degrees of freedom in the numerator and 12 degrees of freedom in the denominator. All right, so for your lower F value, I'm going to use the f.dist command, not the right tail, because I'm trying to do the lower one. This is going to be the left tail. All right, f.dist. All right, so, nope, not f.dist, sorry. F.inverse, sorry. My apologies. I need the f.inverse command because I need the critical value associated with a particular probability. So let's assume that the alpha is 0.05 here, for lack of a better assumption. I'm doing a two-tailed test, so I have to split the alpha in half. So I'll have 0.025 here. We just said the numerator degrees of freedom is going to be 8, and the denominator degrees of freedom is going to be 12. So we get 0.238 for that one. For the upper, we'll do the f.inverse right tail. Again, having split the 0.05 in half, we'll have a 0.025 up in the upper tail. That's why I'm using the right-tailed one, so I don't have to try to do any subtraction. I can just put in the amount that I want. Again, Numerator degrees of freedom is 8. Denominator degrees of freedom is 12. So those are our lower and upper critical values for this two-tailed test. Okay? All right, so since I did 8 and 12 for numerator and denominator, that means I was using x to be the numerator and y to be the denominator. So when I do the test statistic, I want to take the x sample variance and divide it by the y sample variance. And I get 0.362-ish. So that tells us that the test statistic is not in our critical region. Our critical region would be either below this value or above this value, either below the 0.24-ish or above the 3.5-ish. Okay? This is not in the critical region, so we do not reject H naught. So in this case, there's not sufficient evidence to conclude the variances are unequal, so that our assumption that the variances are equal is an okay assumption to make if we're doing a test to see whether or not the means are equal or not. So that's the idea for your F test. We will do more examples. We're going to go on to new material when we start talking tomorrow or later today, depending on when you're watching this. But we're going to do new stuff. But this goes along with the old stuff. It's pretty straightforward how to do it. You just have to remember how to get your F values out of Excel. I'm going to expect you to do these in Excel anyway. So anyway, I will see you hopefully tomorrow when we talk about new stuff in section 7.5.